Good morning, everyone. Today, lecture 6, our sixth lectures of Advanced Artificial Intelligence that we heard for Master Studies, Computer Software Department in College of Computer Science and Information Technology in Wasit University. And today is 13 April of the 2025 year. In this lecture, we will present the chapter 4 of this book's Artificial Intelligence Structures and Strategies for Complex Problem Solving for George Dheyaa. And this chapter 4 focus about heuristic search. And we remember in the previous lectures, we explained or presented the search and knowledge representation, where the artificial intelligence consists of two parts. First part, presentations or knowledge representation, and the second part, search about the space problem. In traditional search, or called blind search, where there is no information about the guide to inform me for selecting the suitable branch in the problem state. And we study in the search 4 strategies. We have depth and breadth, search, and others, so on. All of these strategies search from these initial states and reaching the goal state or goal state without any information about selecting or which branch we select. This searching called blind. But when the problem states or state space of the problem complex and have many branches that guide us to the suitable goal, in this case, if we using this blinding or traditional blind search, we may either impossible or we have wasting time because the complexity of the structures. Thus, we must focus on other manner to guide us for selecting the suitable branch and get us the goal with the best times and with no complexity. This is called heuristic search. In the heuristic search, there is particular value, maybe called heuristic function. This value will be used as the guide for selecting the suitable branch to get the suitable goal. Heuristic function. For example, if someone, patient, go to the doctor and he suffered from particular disease, and his symptoms may be headache and fever and fatigue and so on. Maybe another doctor or person not doctor, maybe he confused it with the disease, with this disease, or selecting which disease, because there is confusion between these symptoms to decide which disease this belongs. But the doctor have experience in his working, maybe select suitable disease and get it treatment or therapy according his algorithm to search, or his algorithm to select the suitable disease. How he is doing this? he used particular function called heuristic search, and this function or this value or this factor guide him to select this manner or this decision from many decisions of disease. If he not using heuristic search or heuristic function, he will be maybe 5 or 6 or 7 and so on of disease. Maybe he will try to test and error and select each one and give him some treatment, and he say with him, go for particular days and return to me and say to me which treatment is correct. And this is maybe time consuming and impossible to use in the real life. Thus he used experience in the heuristic search. And maybe another problem, for example in the chess game, we have one goal. The goal is the checkmate. We have one goal. But if we use the blind search with the complex structure of set space, this will use time-consuming and complex structures of representation for this problem. And this is impossible to be used in the real life, because the time consumed for this problem, to search of problem, there is no computer can solve this problem. Thus, we must select from multiple parts one part of them that guide us to the or reach us to the goal, and that's technique. In this manner, we use heuristic search. Thus, there is two types or two examples. We illustrated why we use heuristic search in the doctor, and the other problem as the chess game. Let's continue. Production and the state space search, heuristics are formalized as the rules for choosing those branches in state space that are most likely to lead to an acceptable problem solution, as we illustrated in the two examples. For example, states or in the chess game, or the doctor. The patient go to the doctor. When we use the heuristic search, the doctor likes to use the rules for selecting one or many branches depending on the particular function called heuristic function in the doctor. Also in the chess game, there is many branches or parts can reach us to the goal, but we select one from these many branches or parts to get the shortest parts and the best solution that reach us to the goal, and the goal in the chess game, the checkmate. This is rules for choosing those branches in the state space that are most likely to lead to the unacceptable problem solution. And there is two basic situations that make us to select or represent the problem of the heuristic search. A problem solves employ heuristic in two basic situations. The doctors and the chess game. The problem may not have an exact solution because of inherent ambiguities in the problem statements or variable data. There is many hypotheses and many decisions for choosing particular disease or decide this is data means the symptoms of the patients, and the same as for the many decision for selecting disease. That's many disease. This is conclusion. Medical diagnosis is an example of this. A given set of symptoms may have several possible causes. Doctor used heuristics to choose the most likely diagnosis and formulated a planned treatment. Now give him treatment or therapy depending on his experience to select particular paths and reach him to this disease. As we say in this example, may have the problem or the patients give with the particular symptoms, for example, headache and fever, joint pains, all these, or headache, all these symptoms may lead us to decide this disease is a flu, simple flu, or maybe this is caused by a more complex disease. Thus, the doctor will use his experience and these simple symptoms or symptoms to decide this is related to this particular disease. This is heuristic search. A problem may have an exact solutions. This is other type in the chess game. Have another exact solution, but the computational cost of finding it may be prohibitive. This is one solution. This is go the checkmate. But the computational cost for finding this solution is high or maybe prohibitive. In many problems such as chess game, safe space growth is computationally or combinatorially explosive, with the number of possible states increasing exponentially or factorially with the depth of the search. Because this complex structures and the search for who will exhaustive search that will cost time, and there is not enough space to represent all this state space in the computer or in the real computer. In these cases, exhaustive cross-mode search techniques such as depth-first or breadth-first search may fail to find a solution within any particular length of time. Heuristics attacks this complexity, guiding the search along the most promising path through the space. A promising path through the space by eliminating unpromising states and their descendants from considerations. A heuristic algorithm can defeat this combinatorial explorations and to find acceptable solution. Gary and Jones of 1979, where they said in his notations, they notes, particular notes about the heuristic search that guide or that describe some highlight points in the heuristic search. The one, heuristics are available. That's meaning heuristic search not guaranteed to get these correct solution. Maybe it gets in the available choosing or selecting. A heuristic is only an informed guess of the next step to be taken in solving problem. It is often based on experience or intuition. Heuristic search, because the main concept of heuristic search is to select or guess to select particular path. This means depends on experience or intuition, as like its doctor. Doctor, if he haven't experienced, maybe he failed to get the suitable path of the search, and his decision will be failed. which will be decision will decide wrong disease. Because heuristic use limited information such as knowledge of the present situations or descriptions of states currently on the open list, they are not always able to predict the exact value of the state space further along in the search. As we remember in the search or the strategies of the search, we use two lists, open and closed. You remember in the previous lecture, we explained the open and the closed list in the search strategies. A heuristic can lead a search algorithm to a suboptimal solution or fail to find any solution at all. This is an inherent limitation of a heuristic search. It cannot be eliminated by the better heuristics or more efficient search algorithm. In the game planning or theorem proving are two of the oldest applications in artificial intelligence. This is some examples or the famous example that we use it in the artificial intelligence, theorem proving and game playing, which is application or the applicable by the artificial intelligence. Both of these require heuristic to prune space of the possible solution, because the problem space, when represented in for theorem proving or game planning, need state space that complex structure. For simplicity, we use a heuristic to prune and reduce the size of the search selection space of the possible solution. Expert systems reach has affirmed the importance of heuristic as the essential component of the problem solving. When a human expert solves a problem, he or she examines the available information and makes a decision. The rule of thumbs, this is the main role of the heuristic search. The expert and selecting suitable paths. Formation. Rule of thumb that human expert uses to solve problems efficiently are largely heuristics in nature. These heuristics are extracted and supervised by the expert system designers. Another example, when you enter this building, this college. This is College of Information, Computer Science and Technology. This building consists of many rooms. For example, you enter it from the main gate of the university, and we want to reach this room in this college. If you're using the traditional search or the blind search for strategies, depth or breadth or breadth or so on, you will begin from the gate or the main gates of the university, and we will reach or the go ahead, and we will contrast with the first building that belongs to the education college, and you enter into this college and searching who the building and not find this building, and continue until we reach this building and enter the first gate and looking for this building for the first or the floor and the second level and reach it with this the time consuming. But if we reach this is type of the blind searching, depth or anyone. But when we get you or give you guide when you reach the main gate of the university, and someone or security or guardman guide you to get this room, he said with you, go ahead and leave the first building and the second level until you, while you reach the third building, this building, and we go to the first level, and the end of this level, we will get this room. This is guide as like the heuristic function. He guide you, not blending. When we searching about this building or this room, we not like climb and go search all the rooms for all the buildings. You leave first and second, we get this building because he informed you to go to this building. This information or this guide represent the heuristic search because he guide you the suitable goal. We think of heuristic search from two perspectives: the measures, heuristic measures, and the algorithm that use heuristic to search the state space. There is two measures or two factors that depending on the heuristic search. The measure, this is function value, and the algorithm, because there is many algorithm will be studied in this chapter. Algorithm, A star algorithm, and cross algorithm, and many so on of algorithm which use it in the heuristic search. Thus, in the heuristic, there is two factors use it: measures and sometimes called heuristic function. This is measure and algorithm. As figured below, we will show in tic-tac-toe state space the combinatory exhaustive sets are high but not insurmountable. Each of 9 best moves has 8 possible responses, which in turn have 7 continuum moves, and so on. As simple as puts the total number of states for exhaustive search at 9 multiply 8 multiply 7 as factorial of 9. This is like this, and shall say is empty, and the tic-tac-toe is empty. We draw 9. This is 9 for this. First one, but either, for example, this the first person will use X. First player will use X. The first person maybe put the X here, or here, or here, or here, and so on. That is 8 or 9 selection in the first level, and the opponent player or other player, after, for example, select this X here, there is 8 example of putting the, for example, O. The other games or the player will use the O, where we will put O either here or here or here, and so on. How many of there? 8. 8 possible. 8 possible. After 8, I will, for example, the use of X. After 8, the X have how many? 7. And so on. Thus, from beginning to the end, we will get to factorial of 8 or 9. This example, this fashion, is the blind search. There is no guide. But if we use heuristic search, we will summarize these from this or these structure for fewer parts. For example, we use the symmetry. Symmetry, for example, where we put X here in this corner, the same as here in the same corner or other corner, and the same for this corner or this corner. The same. where you put here the same things here, the same things here, the same things here. That is four states. We can represent all of them with one and select this. And in the center of the sides, here or here, center of the side, or the center of the side, or center of the side. How many? 1, 2, 3, 4. 4 answer. This one. Now we get this and this. And only one in the center of the grid. Thus we get 3 only. Just like this. The first person, that our first player, we're using X. Either put X here in this corner. This corner, the same kernel here or here or here. Like this. Rotate this, the same. Okay? Or put in the center of the grid, or center of one of the 4 sides. For example, upside here, the same of the right side, the left side, or the right side, or the down side, or bottom side, the same. This is called symmetry. Symmetry of 4. This one, symmetry of 4, and this one, 4 and 4 and 1, 9. We summarize it with the 3 states. And the other, the same things, when we summarize the structures from the complex, this complex, to the simple complex. This is one manner of the heuristic. We use symmetry. The symmetry detection decreases the search space. Many problem configurations are actually equivalent under symmetric operation of the game board. Thus, there are not 9 but really 3 initial movies. 3, not 9. Because this we use 9 summarized to 3. 3 initial movies. 2 corner like this, the same this or this or this. In the center of the side, side 1 or side 4 right, or the center of the left side, or the center of the bottom side, and the center of the grid. Use of symmetry on the second level further reduce the number of paths through the space to 12 multiplied 7 factorial and so on. Simple heuristics, however, can almost, this is another function type or the type of the heuristic. However, can almost eliminate the search entirely. We may move to the stage in which X has the most winning opportunities. For example, if the first one put X, for example, me is the first player, put X here. If X here, how many possibles can I get from this state? This either when I put X here, either I put X here and here, there no, this one solution, or other solution, put X here and here and here, I get this solution or this solution. How many possibles? 3 possibles can I get from this state. And if I get here, how many possibles? This is 1, 2, 3, 4, 5. 1, 2, 3, 4. Sorry, 4. 1, 2, 3, 4. 4 possible. And here, 1, 2. Now, to be intelligent, which one we select or choose? Which one of them? This or this or this? 2 or this? Or 4 or 3? I choose most winning. This most winning. Because this have 4 possible. I will get this. This is guide. This is guide use as heuristic sales guide us to get the paths that lead us to the most winning. From here, this is 3, and this is 4, and this is 2. I will choose these because this will make me win 4 times more orders. This is 3 times, this is 2 times, but this is 4. This is more probability of winning. The first 3 states in the tic-tac-toe game are so measured in the figure below. In case of states with the equal numbers, if we get states equal number, for example, this is 3 and this is 3, for example, which one I will select? I will select the first one I focused, or of the country. If I search from the left to right, I will choose first one with the same number. For example, this is 303. I will get this because the first one. In the case with the equal numbers of potential wins, take the first such states found. The algorithm then selects and moves to the state with the highest number of opportunities. Selects and moves to the state with the highest number of opportunities. Select this. In the case X here, takes the centers of the grid. Take this, the center of the grid X. Note that not only are the other 2 alternative ultimate, but also all over the centers. 2/3 of the whole space is rolled away with the first move. After the first move, now I gave the first move this. The opponents, this is opponent O, can choose either of 2 alternative moves. Now, when I select this and I put X here, now the opponent's player have either put this O here, the same thing here or here or here, one corner, or the center of the sides here or here, here. Thus, when I select this, the opponents to winning have 2 possibles. Either put here or put here. If he puts here, now I have 4 suitable or possible solutions. Either when he put here, either I put X here, or in this corner, or in this side, or in this corner. Now I have 4 possible, and so on. If I select this, the patients or the opponents select this type or this branch, I will evaluate the function. These 3 and these 4. Which one I will select? Select 5. Because 5 more winning, like from here or here. Other is 1. 4. 1, 4, 2, 3, 4. And other. This is half 5. Why? Because it's 1, 2, 3, 4. 5. And if you select this, I will evaluate the, and I find this 5. I will select this. Thus, if you select this, I will select this 5. And we will put O here, I will be select this manner because this is 5 possibles. Also, not exact supervision of the cell size for the most winning strategies for tic-tac. A crude per pound can be computed by assuming a maximum of 5 moves in a game with 5 open options per moves. This crude pound of 25 states is an improvement of 4 orders of magnitude over factorial 9. Now some examples of the algorithms for search, for heuristic search. We are using hill climbing. Hill climbing, this is for the hill climbing strategies expand the current states of the search and evaluate children. The first child is selected for further expansions. Neither its siblings nor its parents are retained. Hill climbing is naming the strategy that might be used by the eager but blind mountain climber. This is thought is given from the blind mountain climber. Mountain climber is when someone he want to climbing the hill or mountain. The manner of the mountain when he climbing, he puts his hand for the shortest, most edge, and he will put her leg upon it, and after that he will select or the search for above and select the most edge, and so on. This is called, for example, when I put my hand or my leg upon the stone, this is called parents, and the other is children's. This is represented as children's, and the same level. When I looking for the same level, this siblings. When I get the best one is the most edge. When I choose it or select it, it will be the parents. And looking for all the children of these parents, and so on. This is called blind mountain climbing. Go uphill along this steepest possible path until you can go no further, because it keeps no history. The algorithms cannot recover from failures of this strategy. An example of the climbing in the factor was the take the state with the most possible widths. When we mapping the manner of the hill climbing in the tic-tac-toe games, the hill climbing will choose the nodes or the states with the most winning. The most winning here will represent in the climbing of the hill climbing as like the most edge. In hill climbing there is some problem called local maximum. Which meaning of the local maximum? Local maximum, that means I reach a particular level and particular nodes and select this node, this have most winning. But this is have most winning only is this level. But in other level, it's not most winning, because these children of these nodes have low level or low winning, and this make stop in the local maximum. A major problem of the climbing strategies is that tendency to become stuck at local maximum. If they reach a state that has a better evaluation than any of its children, the algorithms falters. If this state is not a goal, but just a local maximum, the algorithm may fail to find the best solution. That is performance will improvement in limited settings, but because of the shape of the entire space, it may never reach the overall test. An example of local maxima in games occurs in the puzzle, often in order to move particular tile to its destinations. Other tiles already in goal position need to be moved out. An example of local maxima, for example, here in the third level, I will get this 4, for example, or get to 3. Here, there's 4 and 2. When I get the 2, this is local maximum. Because this lower of this, but lower of this get in the 5 and 4. And wrong choice. And reach the fail of the goal. Maybe go here, but I select this box because I choose this is the most winning, and this most winning lead us to the wrong choice, but the real choice from the other parts. This is called local maximum. Several programs at the 1958 evaluated 40 states with the weighted sums of several different heuristic measures. For example, summation I multiplied xi. The xi in this sum represented features of the game board such as piece advantage, piece locations, control of center ball or proximity to scientific piece for advantage, and even a calculation of moments of inertia of one player's piece about an axis of ball. The A coefficients here of these xi were specially termed weights that tried to model the importance of the factors in the overall or evaluation. It would look ahead in the search space the desired numbers of variables lie and evaluated all of the states at the lab levels with the evaluation of element. Using variations on minimums, it propagated these values back up the graph. The checker player would then move to the best state. After the opponents move, the process would be repeated for the new board states. If the evaluation polygon led to the losing series of moves, the program adjusted its coefficients in the attempt to improve the performance. This is explain how to solve this problem of local maximum. That means we use this coefficients to adjust the variable or the arguments to adjust, but after and adjust for give the best solution after I get or stuck it in the local maximum. If the program won, the opposite was done. Some program thus took a whole climbing approach to learning, attempting to improve performance through local improvements on the evaluation polynomial. Now, the other subject is the dynamic programming. This is another type of the heuristic search. Dynamic program, DP, is sometimes called forward-backward, or when using probabilities, the Verbi algorithm created by Richard Pina, 1956. Dynamic programming addressed the issues of restricted memory search in the problems, composite of the multiple interacting and interrelated subproblems. We demonstrate dynamic programming using two examples, both for text processing. First example, finding optimal global alignment of two strings of characters. And the other examples, finding the minimum edit difference between two strings of characters. First one, suppose we wanted to find the best possible alignments for the characters in the strings. First strings B, A, A, D, D, C, A, B, D, D, A, and the second strings B, B, A, D, C, D, A. One optimal alignments among several possible would be, now, the alignment would be B, A, D, A, D, then D, D, C, C, A, then B, and so on. Now, this is the summarize the alignment with the fewest error or wrong choice. For example, this is wrong, and this is wrong, and this wrong, and this wrong. But this represent the fewest error. We use an array as data structure of dynamic roaming, and its size is 1 more than that length of each string. In our example, 12 and 5, 8. This is example, for example, 11, but we put 12, and this is 7, put it with 8. The value of each row column elements of the array reflects the global alignment success to the point in the matching process. There are 3 possible costs for creating the current state. There is 3 possible. First one, if the character is shifted along in the shorter string for the better possible alignment, the cost is 1 and is ordered by the array's columns. Here we will quit if this only 1 character. If a new character is inserted, the cost is 1 and reflected in the array's row code. And the third possible, if the character to be aligned are different, shift and insert, the cost is 2. Or if they are identical, the cost 0. This is reflected in the array diagram. The increasing plus 1 in the first row and column reflect the continued shifting or inserting of character to the underscores or empty string. Now forward stage. In the forward stage of the dynamic programming algorithm, we fold the array from the upper left corner by considering the partial matching success to the current point of the solution. That is the value of the intrinsic row x and column y, xy, is a function for the minimum alignment problem, the minimum cost of one of the 3 values in this. Either row x minus 1, column y, or row x minus 1, column y minus 1, or row x, column y minus 1. These 3 array locations hold the alignment information up to the present point of the solution. If there is a matching of the character location xy at 0 to the value of location x1 minus 1, y1 minus 1. If there is no match at 2 for shift or insert, and we add 1 by either shifting the shorter character strings or inserting a character. The final solution will be like this. This is forward from the left and so on. Backward stage. Now we will begin by backward fashion. This is begin from here and we will pass like this. Once the array is full, we begin the backward stage of the algorithm that produces particular solutions. That is, from the best alignment possible, we go back through the array to select a specific solution element. We begin this process of the maximum row column value. In our example, is the 6 or row 7 and column 8. Row and column 8 and this like this from here. From there we move back through the array. At each step, selected one of the immediate state predecessor that produces the present state from the forward stage. In one, either the diagonal row or column that produces the system. Whenever where there is a portion decreasing difference as the 6 and 5 near the beginning of the start path, we select the previous diagonals as that is where the match came from. Otherwise, we use the value of the preceding row or column, like this. Here, we get 7 and 6. We get the shortest, like this, 6 for 6. And we will, here 6, we will use for this. 5 the shortest, and this is 5. From 5, I will get 6 and 4. Like this, 6, 6, 5, 4, and 4, and so on. The second examples of The building an intelligence point checker. For example, you might want to determine what words from our set of correctly spelled words based approximate ascertain and recognize strings of characters. A similar approach could be used to determine what noun today strings of phones represent. Word most closely match a given strings of planet. The task of the spell checker is to produce our ordered list of the most likely words from the direct dictionary that you mean to type. The question is then, how can differentiate measures between pairs of strings of characters? Example, the strings you just typed and the character strings of dictionary, where I type and the real character in the dictionary. For each string, we want to produce an ordered list of possibly correct words in the dictionary. For each of these words, we want to numerical measures of how different each word in the from your string. A minimal difference between two strings can be specified as the number of characters in insertion, deletions, and replacements necessary to tell the first string. This course is the second string established. We now implement a dynamic programming (DP) search for determining the minimum edit difference between the two strings of the character. We let intention be the source strings and execution be the target. The edit cost transforming the first string to the second is 1 for character insertion and deletion and 2 for replacement. Deletion plus the insertion. This example of the character of the editing applicable in the software of the office, where you're typing some things, particular words, and sometimes will be drop of list that inform you to correct this word by a particular number of words. This type here used the dynamic programming. Our array for subgoals will again be one character along the edge of the strings. In this case, 10 by 10 as shown in figure below. The array location 2 by 2 is 2. Here 2 by 2 is 2. Because replacement or the making, deletion, plus and insertion is required to turn an I into an example. Figure below gives the full result of blank dynamic algorithm transform intention into execution. Intentions will be transformed to the execution. The value at each location xy in the array is the cost of the minimum editing to the point plus the minimum cost of either an insertion, deletion, or replacement. Thus, the cost of xy is the minimum of the cost x plus 1 y plus cost of the insertion or cost x, for example here, x minus 1 here and y minus like this, plus cost of the replacement or cost of x here and y minus 1 here plus the deletion cost. So the code for this algorithm is function taking the two strings and their length of the returning the minimum and difference cost. This is function source SL target text returns cost ij. Create array cost s string list plus 1 tail list plus 1 cost 0 0 equals 0 and the repeat or for loop I from 1 to s number of SL plus 1 and for j from 1 to TL plus 1 and the cost function calculated by cost ij equal minimum cost I plus 1j plus insertion cost target ij for I minus 1 and so on. Using the result bold things bold character. In figure below, the following edit will translate intention into execution with total cost of 8. Now, execution will begin. I here change, searching and change. X will be in N, and here N will E will be T, and C will be E, and the other N the same thing, like this. T-I-O-N, T-I-O-N, no change. But these will be changed, insertion and change. For example, intention, deletion I, cost 1, here. Intention I. And replace N with the E, here then with the E, cost 2. Replace T with the X, now X, T with X, cost 2. Insert U here, cost 1. Replace N with C, cost 2. Now, the best first search algorithm. Implementing best first search algorithm, implementing heuristic evaluation function, and heuristic search and expert system. Implementing best first search. Best first search uses list to maintain states. Two lists, open and closed. Open to keep track the current print of the search. This is open. And close to record the states already visited. When I visit particular node and go out from this node, it will be put in the closed or inserted in the closed list. And adding states in the algorithm orders the states and open accordingly some heuristic estimating of the closeness to the goal. That means the working will begin in the open by reordering the nodes or the values of the heuristic function in the open that represent the main working of the heuristic search. Thus, each iteration of the loop considers the most promising stage on the open list. Each iteration of the loop considering the most promising, the first one in the open list, because I reordered the value or the nodes according its value, and this reordering represents the main solution of the heuristic, and we get the most promising value. Now this is algorithm. I will explain each one with detail here. At each iteration, best first search removes the first element from the open. We remember this algorithm in the previous lecture. We will begin. Open will get the first state, and close will be empty, and will begin the open. Either open not empty, we'll continue here. Remove the leftmost state from the open. Now, remove the first elements from the open list and put it in the X. Remember, if it meets the goal, okay, condition, the algorithm retains the solution path that leads to the goal and finish the algorithm because I reached the goal. Note that each state retains ancestor information to determine if they had previously been reached by a short-term path and allow the algorithm to retain the final solution. That if X equal goal, then retain the path from the start to X. Else, here, else will begin like this. If the first element on open is not goal, that is mean else, the algorithms apply automatic prediction rules or operate to generate its descendants. Now, generate children of X. If you remember, when in the state A, we remove it from the open A and get its children. Now this generates children of A, B, C, D, remember. And for each child of X, each one, what I do is, the child is not in open closed, put in the up to the child until you open. Now the child of the X, after checking if not is closed, will be inserted in the open list here. And assign the child heuristic value. If a child state is already in open or closed, if he already open or found, the algorithm checks to make sure that the state record the shortest of two partial solution paths. Duplicates are not retained by updating the path history of the nodes on open and closed. When they are rediscovered, the algorithm will find a shortcut path to the goal. Now, this figure will illustrate the tracing of this algorithm. For example, here I and 5 represent the evaluation function of the heuristic search. And here 4, and here 4, 5, and so on. Figure below, these states expanded by the heuristic search algorithms are indicated in the fold, like this. And this fold represents the search in the heuristic. In the first one, you remember when we get the most winning, now most winning 4 and 4 and 6. There is two possible, the same value. Which one I would select? The first one is. Thus I select it. But when I get its children, I get 5, I5. This is not solution. Refused. And go back its parents. I get the other child. This is child C4, it is okay. I will select it. From this C4, I get G4 and G3. Which one I select? The best one is 3. Because 3 is most winning from 3, 4. Because the fewest function. This function is the fewest. I get 3. Now, I get its children because it's X, and get its children and put this in the open O and P3. Which one I select? G2. Because this is 1. The goal of the first search is to find the goal states by looking at the few states as possible. Few states, that's few number. The more informed the heuristic, the fewer states are proceed in finding the goal. Now trace of the for the 6th or the 7th iteration. A trace of the execution of the first search of this graph appears below. Suppose P is the goal state in the graph. Now I look for the P, for example, here. How can I get it? If I search in the blind searching or traditional searching, I would get, for example, depth or breadth, like this. But I will use heuristic to reduce the search. Here, the value. Now, for the first one, 4. But after that's not possible, not suitable. I will refuse it and come back for parents. Again, the first one is 4. Now, there's 2 children, 4 and 3. First one is 3. I choose 3. H is 2 children, and the value is 2 and 3. I will select, oh, this is not the goal, refuse it, and get the other children of the H. Now I get P. P is the goal. Finish the solution. Now would be like this. I think this is finished in the last one. Now, this represents for the As figure below appears the fifth iteration. This represents the fifth iteration. How? In the first iteration, for example, open is A5 and closed empty. Now, like this would be returned with the part, with the dark or the lights color. In the second iteration, evaluate A, open would be B, C, D, and closed would be A5. Thus only A5 will be dark, and B, C, D will be lights. In the third iteration, I will select B. A, B will be open, and the closed will be C, D, and E, F will be. And when I choose this, I will choose C. C will get H3, and this will be dark, and this will be light. And after that, I will select this. This will be closed, and this will be open. In the sixth iteration or fifth iteration, I will get all of them dark like this, and these with light. This is sixth iteration. If I get more iteration, for example, sixth iteration, I will put this in the closed. This will be dark, and light will be like this, and adding IJ with the light, and so on. All this I finish lecture today.